Welcome to the deep dive. Today, we're tackling a really critical area, especially if you're prepping for senior software engineer interviews, making sure systems stay up and running.
Yeah, definitely.
We're going to zero in on how systems that use a layer for replication manage to keep things going even when, individual parts decide to take a break.
Exactly. For senior roles, it's not enough to just build features. You're expected to think about resilience. How do you design systems that can withstand failures and keep serving users?
Right.
We're going to focus specifically on how systems with a designated leader for data replication handle situations where nodes, especially the leader, become unavailable.
Think of this as your fast track to getting comfortable talking about high availability in these kinds of systems. We'll break down the steps involved when things go wrong, both when it's planned maintenance and when it's a complete surprise.
Uh,
By the end of this, you should have a strong understanding of the core ideas and be much better prepared for those technical discussions.
So let's start with the fundamental goal, resilience. We want our systems to continue operating smoothly, even if individual components fail.
That's the dream.
Right. These failures can be sudden, a server crashes, there's a network issue, or they can be planned, like when you need to reboot a machine to apply a critical security update.
Right. Planned downtime for things like security patches is inevitable. You don't want taking a single server offline for essential maintenance to bring down the entire application.
Absolutely not.
So the main aim is to really minimize any impact when a node isn't available, no matter the reason.
Let's look at a relatively simple scenario first. What happens if a follower node fails? In a leader-based replication setup, each follower keeps its own local record of all the data changes it receives from the leader. This is usually stored in like a log file on the follower.
Okay, so each follower has its own history of what's been happening. Now, what if a follower crashes or, I don't know, loses its connection to the leader for a while?
Well, when that follower restarts or the network connection is restored, it can check its local log to see the last data change it processed successfully before the problem occurred.
Ah, okay.
Then it can reconnect to the leader and basically say, hey, I missed everything after this point. Can you send me the updates I don't have?
So it's like asking for a data refresh, a catch-up. The leader then sends over all the data changes that occurred while the follower was offline.
Precisely. Once the follower has processed all those missing changes,
Yeah.
it's back in sync with the leader and can continue receiving the ongoing stream of updates.
So it gets back up to speed.
Yeah, this recovery process for followers is generally pretty robust and is designed to minimize any disruption to the overall system.
That makes sense. The follower just gets back up to speed, but what happens when the leader itself goes down? That feels like a much bigger challenge.
It definitely is. When the leader fails, we enter a more complex process called failover.
Failover.
Essentially, one of the followers needs to step up and take over as the new leader. Then, the entire system needs to be reconfigured so that everyone knows who the new leader is and uses it. There are typically three main steps involved in this failover process.
Okay, let's dive into those steps. What's the first thing that needs to happen?
The first critical step is detecting that the leader has actually failed. Now, as we touched on, a leader can become unavailable for all sorts of reasons: a system crash, a power outage, or even network issues that isolate it from the rest of the system.
So lots of potential causes.
Right. And the difficulty is that there's no perfect way to instantly know the exact cause of the leader's unresponsiveness.
So how do systems usually figure out that the leader is down? Is it just guesswork?
Not exactly guesswork, but it's usually based on timeouts. The different nodes in the system will periodically exchange messages like heartbeats with each other.
Okay.
If a node, and especially the leader, doesn't respond within a certain period, often around 30 seconds, maybe a bit more, maybe less, the other nodes will assume it's no longer active.
30 seconds. Okay.
Yeah, and it's worth noting that this timeout-based detection usually isn't used if the leader is intentionally taken offline for planned maintenance.
Right, because in a planned scenario, the system can probably orchestrate a smoother switch. You know it's happening.
Exactly. You can handle that more gracefully. But for unexpected problems, it's about noticing the silence.
Right. So once the system suspects the leader is down, based on that timeout, what's the next thing that happens?
The second step is choosing a new leader. There are a few different ways this can be done. One common method is through an election process where the remaining replicas vote, and whoever gets a majority becomes the new leader.
Like a democratic election for servers.
Sort of. Another approach involves a designated controller node that steps in and appoints one of the followers as the new leader, more of a top-down approach.
Interesting. So it's either a kind of vote among the followers or a more top-down decision from a controller. Is one way generally better than the other?
Well, generally, the preferred candidate for the new leader is the follower that has received the most recent data changes from the old leader.
Makes sense. You want the most up-to-date one.
Right. This minimizes the potential for data loss, as that follower has the most complete and up-to-date copy of the data. However, getting all the remaining nodes to actually agree on who the new leader should be, that's a fundamental challenge in distributed systems. It's known as the consensus problem.
Ah, consensus. I've heard that term. Sounds complicated.
It is tricky, yeah, because in a distributed environment, you can have unreliable networks, nodes failing at different times, making it hard for everyone to be certain about the state of the entire system simultaneously.
Right. We won't get lost in the weeds of consensus right now, but it's important to understand that it's a core hurdle. So let's say somehow a new leader is chosen. What's the final piece of the failover puzzle?
The final step is reconfiguring the system to actually use this newly elected leader.
Okay.
This means that all the clients, the applications, the users that were previously sending their write requests to the old leader now need to be directed to the new one. There are various ways this request routing can be managed, which could be a whole other deep dive, honestly.
Right.
But the crucial thing is that the system needs to update its understanding of who is in charge of writes. Everyone needs the new address, essentially.
Okay, so all the applications trying to write data need to know the new address, the new leader. What happens if the original leader eventually comes back online? Maybe the network glitch resolved itself. Does it automatically become the leader again?
Not usually, no. That would be risky.
Wow.
The system needs to make sure that the old leader recognizes that a failover has happened and that it's no longer in charge.
Okay.
It should step down and start acting as a follower, receiving data changes from the new leader. If the old leader were to come back and just continue acting as the leader, well, it could lead to serious inconsistencies, especially if it missed some of the writes that were processed by the new leader while it was offline. You could end up with two different versions of the data, which is, yeah, a nightmare scenario.
Definitely a nightmare. This entire failover process sounds really involved, and it seems like there are several points where things could potentially go wrong.
Absolutely. Failover is indeed a period with heightened risk. Let's think about some of the main things that can cause problems. One significant issue arises if the system is using asynchronous replication.
Asynchronous, meaning the leader confirms the write before it's guaranteed to be on all followers.
Exactly. In this setup, the old leader might have acknowledged a write back to the client, but not finished sending it to all its followers before it failed.
So the newly elected leader might not have the absolute most recent data because it might have been one of the followers that hadn't received that last write yet.
Precisely. Asynchronous replication offers performance advantages, faster responses to the client, but it introduces this potential for data loss during failover if not handled carefully. It's a key trade-off.
A trade-off between performance and consistency. How critical is immediate confirmation versus guaranteed durability?
Right. And when the old leader eventually rejoins the cluster, the question becomes, what happens to those write operations that weren't fully replicated? The ones the new leader doesn't know about.
What does happen?
Often, the simplest approach is to just discard them. The old leader comes back, sees it's behind the new leader, and throws away any local changes that weren't replicated.
Ouch, but the user got a confirmation, maybe?
That's the problem. This can violate what users expect about their data. They might have received confirmation that their action was successful, but that information ends up being lost. It really highlights that tension between performance and strong consistency.
That could have really serious consequences, especially if those lost rights represent important transactions like financial ones or something. You mentioned an incident at GitHub that illustrates this kind of problem. What happened there?
Yeah, that incident perfectly shows the dangers of these subtle data inconsistencies during a failover. They promoted a MySQL follower that was slightly behind the old leader to become the new leader.
Okay, so an async replication scenario, likely.
Seems so. Now, this database used an automatically incrementing counter to generate unique IDs for new entries, like primary keys.
Right, common pattern.
But because the new leader's counter hadn't yet reached the same value as the old leader's before it failed, the new leader started reusing ID numbers that had already been assigned to previous entries by the old leader.
Whoa, reusing primary keys, that sounds bad.
It was very bad. The critical insight here is that a failure in one part of the system and the subsequent failover can have unexpected and cascading effects on other seemingly independent components if data consistency isn't rigorously maintained across the entire infrastructure.
So how did reusing IDs cause a problem?
Well, these same unique MySQL IDs were also being used as keys in a separate Redis data store.
Ah, connecting different systems.
Exactly. So when the MySQL database reused an ID, say ID 123, it suddenly pointed to new data, but the Redis store still associated ID 123 with the old data, maybe belonging to a different user entirely.
Oh, no.
Yeah. This resulted in some private user data being incorrectly linked to the wrong accounts and actually exposed to those incorrect users.
Hmm.
It's a powerful reminder of how crucial it is to ensure data integrity across all interconnected parts of a system during a failover scenario.
That's a really striking example of how a seemingly low-level technical detail, like a counter being out of sync, can lead to significant real-world consequences, like data breaches. What other risks are involved in failover?
Another significant risk is a dreaded split brain scenario.
Split brain. Sounds ominous.
It is. This can happen in certain failure situations, particularly with network partitions,
Hmm.
where two different nodes in the system incorrectly believe that they are both the active leader at the same time.
Uh-oh.
Think of it like two generals both thinking they're in command and issuing conflicting orders.
Two leaders simultaneously. That sounds very bad for data integrity.
It is. If both nodes start accepting write requests without any mechanism to resolve these conflicting updates, you're very likely to end up with lost or corrupted data. Imagine two different versions of the same information being written concurrently. Which one is right? How do you merge them? It's often impossible.
Chaos.
Pretty much. As a safety measure, some systems implement a mechanism to shut down one of the nodes if they detect a split brain situation.
Like a fencing mechanism.
Exactly. Essentially saying, if we think there are two leaders, something is fundamentally wrong, and we need to isolate the problem by shutting down one of them. Sometimes they even shut down both just to be safe and stop writes entirely. This highlights the need for robust mechanisms to ensure only one leader is active at any given time.
That sounds like a sensible precaution, even if it means temporary downtime.
It can be, but even this safety mechanism needs to be implemented with extreme care. If the logic for detecting a potential split brain is flawed,
What could happen?
you could end up in a situation where both nodes incorrectly believe there's another leader out there and end up shutting themselves down, bringing the entire system offline when maybe only one needed to, or maybe neither.
Wow. So the fix itself could cause an outage.
Correct. It illustrates the delicate balance between automated safety measures and the potential for them to cause even wider outages if not implemented perfectly.
So even the safeguards need their own safeguards. It seems like choosing the right timeout period for detecting a leader failure, that 30 seconds or whatever you mentioned, is also a really critical decision.
Absolutely. The timeout value presents a really tricky balancing act between responsiveness and stability.
How so?
Well, if you set a long timeout, say several minutes, it means the system will take longer to initiate a failover in the event of a genuine leader failure,
Right. It waits longer, to be sure.
which results in a longer period of downtime where the system might be unresponsive because no leader is accepting writes.
And for users, that translates directly to the service being unavailable for a longer time, which is bad.
Exactly. However, if you set a very short timeout, maybe just a few seconds,
Then you react faster.
you react faster, yes, but you increase the risk of triggering unnecessary failovers. For example, a temporary surge in server load might cause the leader to become briefly unresponsive, just miss a heartbeat or two. Or a brief network hiccup could delay communication packets.
Ah, a false alarm.
Right. And if the system is already under stress due to high load or network problems, an unnecessary failover can actually make the situation worse by adding further instability and disruption while nodes reconfigure.
So you could trigger a failover cascade just because of a temporary blip.
Potentially, yes. Choosing the right timeout is a delicate trade-off. Too long and recovery is slow. Too short, and you risk these cascading failures or unnecessary downtime.
It sounds like finding that perfect timeout value is quite a challenge, often requiring careful observation and fine-tuning based on the specific behavior of the system in production, not just picking a number out of a hat.
It really is, and often it involves ongoing monitoring and adjustment based on the specific characteristics and observed behavior of the system under different load conditions, different network conditions.
Makes sense.
And because of all these complexities and the potential for serious issues with automated failover, the data loss, the split brain risk, the timeout tuning, many operations teams actually prefer to perform failovers manually.
Really? Even if the software has the capability to do it automatically. That's interesting.
Yes. It suggests that human judgment and understanding of the specific context are still highly valued in these critical situations.
Why is that? Why override the automation?
Well, the reasoning is that experienced human operators can often bring more context and a more nuanced understanding to the situation than an automated system relying solely on, say, a predefined timeout.
Mm.
They might be able to look at other monitoring dashboards, check network status, maybe even know about ongoing maintenance elsewhere, and distinguish between a transient network issue and a real server failure. They can potentially avoid an unnecessary and disruptive failover that could actually worsen the situation.
So it's about combining the automation with human oversight and judgment.
In many critical systems, yes. The automation might handle the easy cases, but a human makes the call in ambiguous or high-risk situations.
So ultimately, dealing with node failures and particularly leader failures in distributed systems isn't a simple on-off switch. It's a complex set of trade-offs and considerations.
Precisely. We've explored the challenges posed by node failures themselves, the inherent uncertainties of network communication packets get lost, delayed,
Yeah.
and the fundamental trade-offs between crucial properties like consistency, is the data always correct, durability, is the data saved permanently, availability, is the system responsive, and latency, how fast is it? These aren't isolated problems, but are deeply interconnected challenges that are central to the design and operation of any distributed system.
You change one, it affects the others.
Often, yes. We could easily spend much more time exploring each of these areas: consistency models, consensus algorithms, network partition handling in greater detail.
Well, this has been a really insightful deep dive into the world of leader-based replication and the complexities of ensuring high availability. We've unpacked how follower failures are managed with catch-up mechanisms,
Which is relatively straightforward.
relatively, and then delved into the much more intricate process of leader failover, highlighting the critical steps of detection, election, and reconfiguration.
Mm-hmm.
We've also examined the potential pitfalls from data loss with asynchronous replication, as illustrated by that scary GitHub incident,
A good cautionary tale.
to the risks of split brain and the difficult decisions surrounding timeout configurations.
For anyone preparing for those senior software engineering interviews, understanding these core concepts and the inherent trade-offs is absolutely essential. You'll likely be asked about how you would approach designing reliable systems, how you would handle various failure scenarios.
Right. You need to be able to talk about this stuff intelligently.
Definitely. Being able to discuss these mechanisms and challenges with a solid understanding, acknowledging the trade-offs, will definitely make you stand out.
So as you continue to prepare, here's a really important question to consider, something to mull over. Given all the complexities and the delicate balance of trade-offs we've discussed today, what strategies do you believe are the most critical for designing truly highly available systems in practice?
Good question.
And perhaps relatedly, how would you approach weighing the risks of relying on automatic versus opting for manual failover in different real-world scenarios? Think about different types of applications, maybe.
Yeah, consider the context.
Exactly. Take some time to really think through these points as you continue your exploration of the fascinating world of distributed systems. Thanks for joining us on this deep dive.